Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello. Oh, there you are. Hello, lesson 33, review of the assumptions. Classwork, review exercises. We have covered a great deal of material in Module 1. Our study has included definitions, geometric assumptions, geometric facts, constructions, unknown angle problems and proofs, transformations, and proofs that establish properties we previously took for granted. In the first list below, we compile all of the geometric assumptions we took for granted as part of our reasoning and proofreading process. Though these assumptions were only highlights in lessons, these assumptions form the basis from which all other facts can be derived. Example, the other facts presented in the table. College-level geometry courses often do an in-depth study of the assumptions. The latter tables review the facts associated with problems covered in Module 1. Abbreviations for the facts are within brackets. Geometric assumptions, mathematicians call these axioms. 1. Line. Given any two distinct points, there's exactly one line that contains them. Plane separation. Given a line contained in the plane, the points of the plane that do not lie on the line form two sets called half planes, such that A, each of the sets is convex. B, if P is a point in one of the sets and Q is a point in the other, then PQ, segment PQ or line PQ intersects the line. 3. Distance. To every pair of points A and B, there corresponds a real number distinction, point A comma B greater than or equal to 0, called the distance from A to B. So that A, distance A to B, equals distance B to A. B, distance A to B is greater than or equal to 0, and distance A to B equals 0 if and only if A and B coincide or are the same point. 4. Ruler. Every line has a coordinate system. 5. Plane. Every plane contains at least 3 non-collinear points. 6. Basic rigid motions. Basic rigid motions, for example, rotations, reflections, and translations, have the following properties. A. Any basic rigid motion preserves lines, rays, and segments. That is, for any basic rigid motion of the plane, the image of a line is a line. The image of a ray is a ray. The image of a segment is a segment. B. Any basic rigid motion preserves lengths of segments and angle measures of angles. 7. 180-degree protractor. To every angle AOB, there corresponds a real number, measure of angle AOB, called the degree of measure of the angle with the following properties. A. The measure of angle AOB is between 0 and 180 degrees. B. Let ray OB be a ray on the edge of the half plane H for every R such that R is between 0 and 180 degrees. There's actually exactly one ray, OA, with A in H such that the measure of angle AOB is that R degrees. C. If C is a point in the interior of angle AOB, then the measure of AOC plus the measure of angle COB equals the measure of angle AOB. And D, if two angles, angle BAC and angle CAD, form a linear pair, then they are supplementary. For example, the measure of angle BAC plus the measure of angle CAD is 180 degrees. Parallel postulate. Through a given external point, there is at most one line parallel to a given line. Page 2. Here's the table we were mentioning in the first page. Okay, facts, properties. All right, fact, property. Fact, two angles that form a linear pair are supplementary. Supplementary means they add up to 180 degrees. So the measure of angle B equals 180 minus 33. Minus 133, I mean. So if I subtract those, 7, 10, 10 minus 3 is 7, 7 minus 3 is 4, the 1 minus 1 is 0. The measure of angle B is 47 degrees. Okay, there's fact 1. B, or the second one, the sum of the measures of all adjacent angles formed by 3 or more rays with the same vertex is 360 degrees. Because if I go all the way around, that's a full circle, 360 degree rotation, if you will. So 133 plus 147 plus G equals 360. So the first thing you do is add the 133 and 147. 7 plus 3 is 10. 4 plus 3 is 7 plus 1 is 8. 1 plus 1 is 2. So then I take 360 minus 280 and I get 0 to 16 minus 8 is 8. So G equals, or the measure of angle G equals 80 degrees. Okay, all right. Vertical angles have equal measures. Use the fact that linear pairs form supplementary angles to prove that vertical angles are equal in measure. So you could say the measure of angle A plus the measure of angle B equals 180 degrees. Okay, but you're probably saying, well, where's A and B? So I need to have a diagram in this one. So if I have just a simple setup like this, then I will put A here and B here. So now looking over here, the measure of angle A plus the measure of angle B equals 180 degrees. If I keep naming these, let's call this C and let's call this D. So the measure of angle A plus B equals 180. The measure of angle B plus the measure of angle C equals 180 degrees. And then I can look over on this side, well, the measure of angle C plus the measure of angle D equals 180 degrees. And finally, the measure of angle D plus the measure of angle A equals 180 degrees. Okay. There's more we can say about this. Let me keep going. So let me move these up. So after going all the way around and showing every single linear pair like I have done, you can also say, let's see, the measure of angle D plus the measure of angle A, not D twice, the measure of angle A equals the measure of angle C plus the measure of angle B. So D plus A equals C plus B. Okay, we could also say the measure of angle D plus the measure of angle A equals, let's see, D plus A equals the measure of angle B plus the measure of angle A. So D plus A equals B plus A. And therefore, we can conclude the measure of angle D equals the measure of angle B. Since they're both equal to A, they're equal to each other. So that's a whole bunch of truths there, knowing that these are straight lines and equal measures, vertical angles are equal in measure. And we use the fact that linear pairs form supplementary angles to prove this. So you can use any one of these angles, and then we could finally conclude that the measure of angle A is equal to the measure of angle C as well. Okay. The bisector of an angle is a ray in the interior of the angle such that the two adjacent angles formed by it have equal measures. So what they're saying here is, if I have a ray, BC, it's right here, there's ray BC. I now know that the measure of angle ABC is equal to the measure of angle CBD. Okay. So now it says, in the diagram below, BC bisects ABD, which measures 64 degrees. So what they're saying is this entire piece is 64 degrees. So what is the measure of angle ABC? Well, the measure of angle ABC equals 64 degrees. And since it's cut in half, it's divided by 2. And therefore, the measure of angle ABC is 32 degrees. The perpendicular bisector of a line segment, is the line that passes through the midpoint of a line segment and is perpendicular to the line segment. The perpendicular bisector of a segment. So AB is a segment. CD is a perpendicular bisector. It passes through the midpoint of a segment that is perpendicular to the line segment. So then they meet at right here, and this is 90 degrees since it's perpendicular. So it says in the diagram below, DC is the perpendicular bisector of AB, and CE is an angle bisector of angle ACD. Find the measure of AC and angle ECD. So they want to know this, and they want to know the length of this. Okay, so for starters, the measure of CB is given as 12. And since this is a bisector, it cuts AB into two congruent pieces. So AC is 12 centimeters. And if this is 90 degrees and the sum of the measures of a line is 180, in other words, this angle plus this angle plus this angle equals 180, and this is 90, then this angle plus this angle equals 90. And this is a bisector, so this is 45 degrees because it's half of 90. This is 45 degrees because it's half of 90. So 45 plus 45 is 90, and 90 plus 90 is 180. So we would say AC equals 12 centimeters, and the measure of angle ECD equals 45 degrees. Okay. Okay, we're continuing with a table of review for page 2, and it says the sum of the three angled measures of any triangle is 180 degrees. That's the triangle sum theorem. So this says, given the labeled figure below, find the measure of angle DEB and ACE. So they want this angle here, and they want this angle here. We're given this is 130 degrees. So this is a straight line. There's two ways we can do this. This is an exterior angle, and this is a linear pair. To get the exterior angle, remember that these are remote interiors. So 65 plus x, if you will, equals 130. So I'll do my work over here, and I'd say 130 degrees equals 65 degrees plus x degrees. Subtract 65 from both sides. This is doing the remote interior theorem. And 10 minus 5 is 5, and 12 minus 6 is 6. And so x is 65 degrees. 65 plus 65 is 130. So I now know that this is 65 degrees. Okay. Then it says, what is this angle here? Well, then we have a triangle sum theorem. So this is equal to this. Why did I change colors? I have no idea. So these are equal in measure. And then we have a triangle sum theorem. So 65 plus 65 is 130. So this has to be 50 degrees. So let me just put that in there. This is 50 degrees because, wow, try that again. 65 degrees. It's a very small area to write. 50 degrees. 50 plus 130 is 180 degrees. Vertical angles are congruent, so this is now 50 degrees. So I would say the measure of angle DEB equals DEB, 50 degrees. The measure of angle ACE equals ACE is 65 degrees. Okay. Because the measure of DEB plus the measure of DEB plus the measure of DEA is 180 degrees. That's the other way we could have done that, okay? So this is 150 degrees. The sum of three angle measures of any triangle is 180. That's how we got this, okay? 130 plus 50 is 180. So this is 50, and then we would say 65 plus 50 plus 65 is 180. So there's all kinds of stuff going on there. There's many ways we can solve these. Okay, continuing on. When one angle of a triangle is a right angle, the sum of the measures of the other two is 90 degrees. Okay, well, that's makes sense because here, let me do this right. Let me get a shape. Let me bring in a right triangle. So all they're saying here is if this is 90 degrees and the sum of a triangle is 180, well, 180 minus 90 is 90. So angle here, call it A, and this angle here, call it B. A plus B has to add up to 90. The fact follows directly from the preceding one. How is simple arithmetic used to extend the angle sum of a triangle property to justify this property? Okay, well, that's kind of a wordy statement here, so let me bring that in. Okay, since a right angle is 90 degrees and angles of a triangle sum to 180, by arithmetic, the other two angles must add up to 90 degrees. Okay. An exterior angle of a triangle is equal to the sum of its two opposite interiors. So I kind of set that up here. I revisited that. That's here as well. In the diagram below, how is the exterior angle of a triangle property proved? Okay, so again, this is lengthy. Let me bring it in. Okay. Okay, the sum of two interior opposite angles and the third angle of a triangle is 180. So they're saying this plus this, the sum of two interior opposite angles and the third angle, this one, adds up to 180, which is equal to the angle sum of the third angle and the exterior angle. Thus, the exterior angle of a triangle is equal to the sum of the interior opposite angles. The sum of two interior opposite angles and the third angle of a triangle is 180. So these three add up to 180, which is equal to the angle sum of the third angle, this angle here, and the exterior, this one. Okay, so if this plus this equals 180, and this plus this equals 180, or this equals, yeah, this plus this equals 180, then this has to equal this plus this. That's what this is saying. Lots of this is going on. Okay. Base angles of an isosceles triangle are congruent. The triangle in the figure above is isosceles. So let me get all this out of the way. This is an isosceles triangle. So in other words, this angle, this side equals this side. How do we know this? Well, if this is 130, this is 50 degrees. And 65 plus 50, and remember, remote interiors add up to this. So this has to be 65 because 65 plus 65 is 130. So 65 and 65, the triangle figure above is isosceles. How do we know this? Base angles of an isosceles triangle are congruent. So we would say what I just said, base angles are congruent, or the base angles are equal in measure. All right, all angles in an equilateral triangle have equal measure. Equilateral triangle. If the figure above is changed slightly, it can be used to demonstrate the equilateral triangle property. So they adjusted AB, they moved it this way to reduce the angle measure of A down to 60 degrees. So they moved AB, rotated B negative, or down, I should say, 5 degrees to get this angle to drop from 65 to 60 degrees. Okay, and in doing so, this also changed to 60 degrees. And now this angle here is 120 degrees. So 60 plus 60 is 120. So these two add up to the exterior angle. This angle here is a linear pair. 120 plus 60 is 180. So now we have 60, 60, 60. 60 times 3 is 180 degrees. Okay, so what we would say here is the measure of angle AEC is 60 degrees, which I've already stated. The measure of AEC is 60 degrees. Okay, AEC is this interior, or this angle here, the vertical. Okay, it's 60 degrees. The measure of angle C is also 60 degrees by angle sum of triangle property. Thus, each interior angle is 60 degrees. Here we go to page 4. The facts and properties in the immediately preceding table relate to angles and triangles. In the table below, we review facts and properties related to parallel lines and transversals. Okay, so here we go. If a transversal intersects two parallel lines, then the measures of the corresponding angles are equal. Why does the property specify parallel lines? Okay, so it says if the lines are not parallel, then the corresponding angles are not congruent. So let me give you an example. If I had a segment like this, and then I had another segment like this, obviously they're not parallel, they're getting closer. Draw a transversal now. This angle, switch to my pen. This angle here is now no longer congruent to that angle. This one's obviously smaller. You can see it's smaller. And I can prove that by just rotating this. So if I made it perpendicular, okay, so now this angle is 90 degrees. This angle's obviously not 90 degrees, so therefore they're not parallel. Okay. All right. If a transversal intersects two lines such that the measures of the corresponding angles are equal, then the lines are parallel. That's the converse of the previous, and here it says it. The converse of a statement turns the relevant property into an if and only if relationship. Explain how this is related to the guiding question about corresponding angles. The answer to that is if and only if. The if and only if specifies the only case in which corresponding angles are congruent when two lines are parallel. Okay, if a transversal intersects two parallel lines, here's a diagram, then the interior angles of the same side of the transversal are supplementary. So that means they add up to 180 degrees. So given this diagram, two angles inside on the same side of the transversal, same side interior angles are supplementary. So the measure of angle H here plus the measure of this angle would be 180 degrees. The property is proved using, in part, the corresponding angles property. Use the diagram below. AB is parallel to CD to prove that angle AG and angle CHG are supplementary. So now they're just talking about the side on the left here. And in order to do so, this is a straight line. So this angle plus this angle has to add up to 180 degrees. So this angle is 110 degrees because 70 plus 110 is 180. This angle and this angle are vertical, so that's 70. So that also proves that's 110. And then coming down to here, we just proved in the prior that these are supplementary. So this has to be 70 degrees because same side interior angles are supplementary. It says it right up here. And then linear pairs, this has to be 110 degrees. Okay, so this says the measure of angle AGH, I think it said. Just a moment, my computer screen jumped. The measure of angle AGH is 110 degrees because they form a linear pair. And the measure of angle CHG is 70 degrees. CHG is 70 degrees because corresponding angles, this 70 and this 70. Thus, interior angles on the same side are supplementary, 110, 70. So I didn't really need this. Okay. If a transversal intersects two lines such that the same side interior angles are supplementary, then the linear lines are parallel. So this is the converse of up here. Given the labeled diagram below, prove that AB is parallel to CD. All right, so this is going to say, it keeps jumping like that, I don't know why. All right, the measure of angle AGH is right here, is 110 degrees because these two angles are supplementary due to a linear pair. And the measure of angle GHG is 70 degrees due to vertical angles being congruent. Then AB is parallel to CD because the corresponding angles are congruent. So now that this angle is congruent to this angle, we know that AB is parallel to CD. Okay? Next one. If a transversal intersects two parallel lines, then the measure of the alternate interior angles are equal. So looking back up at this diagram above here, what they're talking about now is these two angles. Alternate interior, not alternate exterior. So they're not talking about that. They're saying this is 70 degrees because that's vertical. This is 70 degrees because they're vertical. And so now the alternate interior angles, this angle and this angle, are both 70 degrees. 1, name both pairs of alternate interior angles in the diagram above. Okay, so if I name them, angle AGH and angle EHD are alternate interior. That's here and here. And angle CHG here, and angle BGH, which is here. So there's different ways we can name them. So, oops, let me go up a little higher. Angle CHG, CHG, or GHC, GHC. So they went from here to here to here, this green angle. And angle HGB, HGB. So that's the green ones. Angle AGH, angle DHG, DHG, the red. How many different angle measures are in the diagram? So you have 70, you have 70, you have 70, you have 70, you have 110, you have 110. This is 110, this is 110, adding up to 180, adding up to 180. This is 70, this is 70, this is 110, this is 110. So when I label all of these because of linear pairs and corresponding angles and alternate interior angles and vertical angles, then we only have 2 angle measures in a diagram when we have parallel lines. Okay, if a transversal intersects two lines such that the measures of the alternate interior angles are equal, then the lines are parallel. That is now the converse of the prior. Although not specifically stated here, the property also applies to alternate exterior angles. Why is this true? And the reason is the alternate exterior angles are vertical angles to the alternate interior. So the alternate interior, 70, 70, vertical angles are congruent. So if alternate interiors are congruent, then alternate exteriors must be because of the vertical angle theorem. Okay. Okay, page 5 brings us to the end of lesson 33. This is a really good summary of what we've done so far. These are great tables in the last 3 pages to review for any end of unit test. So being the end of lesson 33, go do your problem set.